Hello everybody, my name is Peter Klapper from the School of Biosciences at the University of Kent. In this clip I want to show you how we can use a Lineweaver Burk plot for data analysis if we want to find out the characteristic parameters of an enzyme. So here's the problem. You are a research scientist and you study an enzyme and you want to characterize it a little bit further. And to do so, you measure initial velocities in an enzyme reaction at different substrate concentrations. And what you want to know is, what is my Vmax? Or in other words, how does this enzyme behave when the substrate concentration is very high? What is the Vmax over Km? Or in other words, how does the enzyme behave if the substrate concentrations are very low? And last but not least, what is the affinity of the enzyme? What is the Km? And as I said, you've got your data here, so you use different substrate concentrations and you measured the corresponding initial velocities. So far so good. So what do we need to do? Before we get going, it's always a good idea to find out what we should expect actually. And what we can very easily do is we can say, right, what do we expect for our Vmax? Now we know that our Vmax must be larger than our largest initial velocity. So it must be larger than this one here. So maybe we can say Vmax might be in the order of, say, around 45 millimolar per minute. So we can probably say, well, perhaps this is our Vmax. Now, what would be our Km? Well, we know that Km is defined as the substrate concentration, which gives us exactly half of Vmax. So all we need to find is basically the substrate concentration that gives us half of Vmax. Well, half of Vmax is 45 millimolar per minute, so half of Vmax would be 22.5, this one here, that's half of Vmax. And the corresponding substrate concentration would be 10 millimolar. So that is, here is substrate concentration. And therefore we can say we estimate Km to be in the order of 10 millimolar. Because this substrate concentration of 10 millimolar gives us half of Vmax. And we can very easily calculate from these data our Vmax over Km. This is the enzyme parameter that tells us how the enzyme behaves at very low substrate concentration. So we've got 45 millimolar per minute divided by 10 millimolar. And from that we would get 4.5. We can easily leave the units as millimolar per minute divided by millimolar, or we can cancel out the millimolar. So in this case it would be minute to the -1. So these are our guesstimates. And here again, so that we don't forget, 45 millimolar for the Vmax, 10 millimolar for the Km, and 4.5 millimolar per minute divided by millimolar for the Vmax over Km. So what can we do now? Obviously, this was just a guesstimate, and we want to know what actually our data are. And for this, in this case, we want to use a Lineweaver Burk plot. Just to remember, in a Lineweaver Burk plot, we actually calculate one over rate versus 1 over substrate. That is what we use. So what do we need to do? Well, first of all, we need to take our substrate here our substrate concentrations. These are these concentrations here. And we have to calculate 1 divided by the substrate concentration. So we've got, for the first entry, we have 1 divided by 3. That's the substrate concentration, equals 0.3. For the second one, we've got 1 divided by substrate concentration is 5 equals 0.2. And we do exactly the same thing for the initial velocities. This one here. So we calculate 1 divided by 10.4 equals 0.1. We do the last one here, 1 divided by 40.5, and that gives us around 0.02. So these are the data, and we leave the data on the side here. And then we draw our graph. So what we do in this case is we have to label our axis. So what we plot is 1 over the rate, that's on the y-axis here. And of course the unit, if we do 1 over rate, would be minutes per millimolar. So that is exactly 1 divided by millimolar divided by minutes, and I can write this as minutes per millimolar. Likewise, on the x-axis, we plot 1 over the substrate concentration. So this would be the substrate concentration is given in millimolar, so the unit for the x-axis would be 1 over millimolar. And all I need to do now is really plot the data, which I've got here and here. So for example 0.01 and 0.02, and what that gives me, for example here, so for this one here I've got 0.01, that would be somewhere here, 0.01, and the corresponding 1 over V, that would be 0.02. So that actually gives me this point here. And if I do that for another point, say this one and this one, so I've got as a substrate, as a 1 over substrate concentration, I've got 0.03, so that would be around here, and the corresponding 1 over velocity would give me this point here. And all I need to do really is to then draw a straight line, something like that, and I got basically all the things that I need to know. Now from a Lineweaver Burk plot we know what the data actually represent and how we can find these data. So first of all, we know that the intercept here between the y-axis and our line, this here gives us 1 over Vmax. And in this case it's not terribly easy to read this. It's probably, this gives us 0.016 minutes per millimolar. And you see that's already the first problem with this kind of plot. It's not very easy to find these rather small numbers here. Now this point here, this intercept here, gives us minus 1 over km. And again, it's not very easy to read this, so that's 0.05 minus 0.05 minus 0.1. And again, not terribly easy to read that. And the gradient here, this gradient would give us Km over Vmax. Now notice it is not Vmax over Km, which we usually want to find out. It is Km over Vmax. And it's the same thing for the Vmax. With the Lineweaver Burk plot, we do not get a Vmax, we get always the reciprocal numbers that we want. So 1 over Vmax, Km over Vmax, and 1 over Km, and in this case minus 1 over Km. So we can try to find out these numbers, and for the Km, Vmax over Km, or Km over Vmax, what we have here, in this case, we would get probably something for this gradient here. We get something like, well, 4.3 millimolar per minute. So in the next one, again, here we've got our 1 over Vmax, and here minus 1 over Km. So if we do our calculations, we get the following data. For the Lineweaver Burk plot, we get a Vmax of 62.5 millimolar. Note, in the plot we get it as 1 over Vmax, and we have to calculate it backwards again in order to get our Vmax, because we are not interested in a 1 over Vmax, we want to know the Vmax. So if we do that, we get 62.5 millimolar per minute. Now our guesstimate was 45 millimolar per minute, so we are in the same range, but not absolutely identical. For the Km, we got 14 millimolar from the plot, and we estimated it to 10 millimolar. And Vmax over Km, we got 4.3 millimolar per minute and millimolar, and in our guesstimate we had 4.5 millimolar per minute. So who is right? Obviously, these data are within similar range, but there is a considerable difference between them. And when I designed this data, I actually used these data here for estimate. These guesstimate data are pretty accurate actually. And I used this data to define our experimental graphs or data. And what you can see is that the Lineweaver Burk data that we got here, despite being very careful in the plotting, are not terribly accurate. And that is one of the big problems with the Lineweaver Burk plot, that everything is 1 over, and the mathematical error by converting these things and reading good data from a Lineweaver Burk plot introduces a huge error. And therefore, Lineweaver Burk plots are in general not terribly good to find out the characteristic enzyme parameters. Despite this, and having said that, Lineweaver Burk plots are incredibly popular with textbooks and with biochemists, but as you probably have seen, Lineweaver Burk plots are not very accurate, and I suggest that you stay clear of Lineweaver Burk plots and don't use them, because they are simply not accurate enough, and they have a bunch of other problems. They show data crowding, and you have to design your plot very carefully. So hands off Lineweaver Burk plots. I suggest that you really use something like an 80-Hofstade plot, or perhaps even a linear direct plot, and because these plots have huge advantages. So I hope this was helpful, and thank you for watching it.